Hi, everyone. I'm Isam Laraji. I'm one of the co-organizers of this workshop. I'm here to introduce some of the speakers. So here we have Hazel Doughty. She's a postdoc at the University of Amsterdam, working with Professor C. Snook. Is that how it's pronounced? Okay. She completed her PhD at the University of Bristol in the UK under the guidance of Professor Dima Dame. During her PhD, she spent several months as a visiting researcher at INRIA Paris. In September, she will join the University of Leiden as an assistant professor. Her research focuses on video understanding, such as fine-grained understanding and learning with incomplete supervision. The floor is yours.
Thank you. Thank you very much for the introduction. And as you said, I'll be talking a bit about how to reduce supervision in video understanding, particularly for detailed video understanding. So we heard a bit about the general motivation for learning from limited labels, but I wanted to spend a bit of time just saying what my motivation is. And kind of my general aim is to understand videos in a detailed way. So we've already had a lot of progress in this field where instead of describing all these 3 videos as performing CPR, we can now describe in more detail what is happening in each stage and say specifically the action label. And my goal is to give a bit more detail, maybe describe how, but generally have a bit more detail of like the adverbs, the prepositions, the other verbs that are going on as well. And obviously to increase the detail, we need to increase the length of the label, which then increases the amount of time we need to collect the labels in the wild. And already with these kind of short action labels, you need a lot of well-curated data to at least test the model and likely to learn from as well. So when I'm trying to increase the length of these labels and get them more detailed, it's really important to then reduce the amount of these labels we need to collect. So like I said, my aim is to increase detail, and to do that, I think it's necessary to try and decrease the supervision. And I've got a few different works along these 2 axes, and I'm going to highlight 2 in particular today, which is generalizing to new domains in video and learning from self-supervised video. So I'll start with learning from video in a self-supervised way. And as I'm sure you all know, the way you do self-supervision is generally to learn from a large amount of unlabeled data using some pretext task. Maybe this pretext task is to predict some property of the data, use contrastive learning, video MAE, doesn't really matter. But the idea is to just learn this representation. Then you can transfer this representation and model and fine tune it with a hopefully small amount of labeled data. And this really becomes useful when you're reusing this representation and when you'll be able to adapt this representation with a small amount of data. If you think about this problem, yeah, it's great because you can use self-supervision and that doesn't require labels, but you're still using a large amount of labels to do this fine tuning. So how can we kind of try and reduce this a bit more? So in video, we were thinking about, okay, how are these self-supervised models currently used? And generally you pre-train on a large data set like kinetics and fine tune on these other 2 data sets that are actually very similar. So they're similar in the source of the data, the kind of actions they contain. And using these has allowed some really great progress in this field. But really to make use of self-supervision, we want these models to be able to adapt to different kinds of scenarios. So we set out to do this study, and this work published at ECCB last year, where we're looking at a few different factors of how we can generalize these models and try and reduce how often you need to train them. So we first looked at downstream domains and seeing whether these can transfer to different kinds of data sets, different viewpoints, different situations. Downstream samples, so instead of fine tuning with like these giant full data sets and using lots of labels in the fine tuning, see how few labels we can actually use. Downstream actions, so moving from the kind of coarse-grained actions you see in the pre-training data set to more fine-grained and motion-related actions. And tasks, so can we make these models work beyond action recognition? And we did the study, which included over 500 experiments, and I'll highlight like just a few conclusions we had. So I'll do the downstream domains in a bit more detail and just give you the highlights from the rest. So when we look at the domains of these data sets, they're all really quite different. You kind of start with data sets where the background is a lot more useful to determining the action, and then maybe as you go to enter and find Jim, the motions are more important, and then you have data sets like epic and something where the perspective is entirely different. So like I said, I'll highlight the domains. And don't worry about the numbers here. The important thing really to look at is the colors. So orange is worse, blue is better. And as we go from left to right, the data sets increase in granularity. So what we notice first is you get this really nice ranking for UCF. So on the methods we test, they have this nice order. When we move to a different domain, the ranking changes dramatically. So you see a lot more orange in the middle of the ranking and blue because the orders of how well the methods do are changing. We also notice that the benefit for self-supervised pre-training is much lower when the domain changes. So you're only getting like a 1% boost from doing all this really heavy pre-training. When we move even further, so we go to Epic Kitchens, the ranking changes even more. So the data set, the methods that are good on one data set are not necessarily going to be good in a different domain. So generally UCF performance isn't indicative of what's going to happen in the other domains. We do notice there are some methods that do really well, and these tend to be methods that are a bit more motion focused. So RSPNet looks at speed, CTP tries to track patches, and TCLR contrasts different clips within the same video. But these tend to be the winners. Supervised, though, by far is still a lot better to use. So it's still more useful to use all these labels in fine tuning than using these self-supervised pre-training methods. For samples, again, we notice that the ranking changes a lot as you reduce the amount of data. So a method that's good with 8,000 samples is not a method that's good with 1,000 samples. And the same is true for other data sets. For the actions, generally we notice models, when they're pre-trained on kinetics, they tend to do well on the type of actions you're seeing in that data set, so coarse-grained actions, even though they're not seeing the labels in pre-training. For the tasks, though, models do generalize reasonably well, so long as the task's done in the same domain as the pre-training data set. And in general, there's no clear winner. So the methods I showed you that were good at the domains are not necessarily methods that are going to be good at doing tasks or granularity. It changes completely between the different factors we tested. Although supervised is good for all factors. Although we do notice a trend that the ones that kind of a little more motion focused tend to do a bit better. And in this paper, we have like a subset of these experiments, so you can test your own video self-supervised model and see how it generalizes across these factors. Okay, so that kind of showed us that there isn't a model that is good at this kind of generalization across all these factors, which really limits the kind of usefulness of them because you're having to pre-train on different data sets for different situations. So how can we make a model that is generalizable to all of these things and uses a small amount of data to fine tune so we can really reduce the supervision even further? So that's what we set about doing. And to kind of create this, we looked at what like the standard way of doing contrasted learning video was. And that is, here you've got two pairs. So you take different crops of the video, maybe like a temporal crop. So you're comparing the first second of video to the third second of video, and you're saying these are similar. So in the example on the left, you've got two videos of someone doing golf because they come from the same video clip. And you've got to say, okay, these are similar. They're different from these other videos, which are again similar in turn. And the way we want that to work is, okay, these are two videos of people doing the same action, therefore they should be similar. But what's actually happening, as you can see, is they look really similar spatially. So the background's the same, even if you're not looking at what the person's actually doing. So there's kind of a spatial shortcut to this task. So what we try to do is inject motions into these videos so we can learn the similarity between the motions rather than the background. So as opposed to contrasting two clips, learning the similarity between two clips of the same video, we're now learning the similarity between two different videos with the same motion injected into them. And I'll explain a bit more how we do that. So we get a pair of videos, we take a patch from one of the videos. We replicate the patch in time for the number of frames of the video we've got, and we give this patch some motion by translating it various points within the video frame. And then make the motion a bit more complicated by adding factors like scaling and rotations. We then copy this like created tubelet back into the two videos. So the only similarity is now the patch and how the patch moves throughout the video. Then we can learn the similarity between these, and the hope is that then it learns the motions because that is the most similar part of the two videos because the background video is completely different. So these are just some examples of the kind of motions we're creating. Generally quite smooth motions, and with scaling, rotation, and shearing as well. So we have a look at what the model learns before we do any fine tuning, and we do find it is more sensitive to the motions. So if you look on the left, that's kind of what the old way of doing it. The baseline is, it's looking at objects in the background with the red heat map. In ours, it tends to look at where the person's doing. And this is before it's even seen any of the fine gym data. It is just naturally a lot more sensitive to motion. So it picks up on the regions where the motions are happening. Again, in a different domain, UCS is a bit more similar to the training data set. So the baseline's a little bit better, but ours is a lot more focused on where the motions are happening. And so when we're learning this similarity, there's kind of two aspects that are similar. There's the spatial similarity of the patch itself and the actual motion it has. So we wanted to see how important the spatial similarity is and how much it's relying on the motion. So if you look at the, compare the bar in blue to the bar in green, that's when we only add the spatial similarity, and then it decreases. When we add the yellow bar with the motions, that's when the model starts to work. And what we find is because we're injecting these motions into the videos, we're in a way of creating new videos. So actually we can learn the pre-training with a lot less data. So even with only 25% of the data, we're still getting a very similar result. So we can even skip a lot of the pre-training step. And it's the same for fine-tuning on other data sets. Okay, so going back to the benchmark we had before, how does this model do? So it does do reasonably well on these like kind of old ways of doing things, because even though it's learning motions in the pre-training, it's able to easily add the spatial aspect in the fine-tuning. Then on these factors we were looking at for generalization, it improves on domains, it improves on downstream samples, so we're able to learn with fewer labels in fine-tuning. It does really well on the actions because it's focusing on these motions, and these fine-grained action data sets tend to be motion-focused. But where it doesn't work so well is the tasks. So it's still kind of limited to action recognition. Okay, so this concludes the self-supervised work. We've kind of made this model that's able to generalize a bit better, but there's still a lot of different factors you can do, and in terms of generalization and further work to try and reduce the labeled data it's trying to learn from. Now I'll talk a bit about the specifically focusing on generalizing to new domains. Okay, so I talked a bit about domain shift in the previous work, but just to explain a bit further, the idea when we're trying to adapt between domains is we maybe have a model that works in the kind of environment in the top, and we want to make it work in the environment in the bottom as well. And this is a kind of domain shift related to the scenery. Yeah, and we've got other types of domain shift as well. So maybe the camera viewpoint changes, maybe the actor that's performing the action changes. And we want to be able to have a model that can tackle all these different types of domain shift. Okay, so how do we learn this? The standard way of doing domain adaptation is you have a source domain with labeled data, you have a target domain with unlabeled data, and you want to learn a classifier from the labels in the source domain that also applies in the target domain. So I'll explain a bit how we do this in video specifically. What we notice is that the scenery and environment and visual features change a lot, but the action sound changes less. So maybe some of you can hear from my laptop, if not, you can imagine. The sounds between them are a lot more similar. So we use the audio in two ways. One is balancing the types of interactions we have. So yes, you have the same actions in the target domain as in the source domain, even though in the target domain they're unlabeled, but they don't necessarily follow the same distribution. Some are going to be much more rare than others. So we use the audio to kind of cluster the different types of interactions we have so we can then balance them between source and target and end up with these clusters. So here's an example of one cluster. You see, even though it's mostly clustering these based on audio rather than the visual features, it's picking up similar visual looking things because they're people putting down plates and bowls. The other key way we use audio is to tell us what's not happening. So there's many actions such as this one, which don't have a particular sound because someone's just picking something up, it doesn't make a noise. But what we can tell is that there are certain actions it's not. So because we don't hear water, we know it's not washing, we know it's not closing and stirring because we don't hear the noises from these actions. So we can label what the action is not. Again, here we have an example of the person pouring. And we know it's not washing, stirring, or chopping because we don't hear the sounds related to those actions. So those are kind of the key ways we use the audio. We use it to tell us what is not happening in the target domain and use it to balance the source domain so we can learn a more transferable representation. And then with this, we can learn a transformer that works on both source and target domains. And we also add a domain embedding to reduce the domain shift and a bottleneck for the audio features to help with learning. And what is interesting about this is, okay, of course it works on the three types of domain shift we were trying to make it work on. So the scenery shift, the viewpoint shift, and the actor shift, which is not shown here. But what is interesting is even when we don't use audio in testing, just by using the audio in training, we've learned a more generalizable representation. So it already improves results. Okay, so that works reasonably well. But if we think about how we're doing this domain adaptation framework, we're actually still using a lot of kind of supervision that's sneaking through. So in the source data, of course, we need labels. We have like actions like walk and cut. But in the target data, we need these actions still. We don't necessarily need them in the same distribution as they are in the source, but we still need examples of people walking and people cutting so we can learn this classifier, which is sometimes an unrealistic requirement. So we kind of want to relax this and change what is in our target, unlabeled target training data. So can we use examples of people doing different actions or maybe even no actions at all, just data from that target domain? And I'm going to talk about work where we did this, specifically looking at the domain shift between light and dark. And what is particularly interesting about this domain shift is it's continuous. And the examples of the other domain shifts I showed, they're probably also continuous, but it's harder to kind of have this continuity. The really nice thing about the day and dark is naturally in the data you have this continuity. So we started by looking and seeing if current models could already solve this problem just by doing their normal training. And generally, we found they couldn't. So they have very few examples of dark videos. And with these few examples, they can't generalize very well to the dark. Although the higher luminance also has very few examples, but the model works really well on these higher luminance examples. And this is true for other data sets as well, and multiple different models. So what we do is use any data we can get from the dark. So the current data sets generally don't have dark videos available. So we just say, okay, doesn't matter, they don't need to contain actions. We'll just pull what videos in the dark we do have. So these, as you can see from the examples, they're very different to the kind of action data we'd be using before. They're just any videos we can get of what's happening in the dark. And now we try and learn from these. So from the source data, we can do it the standard way, learn a labeled classifier with the standard activity labels. We also want to be able to learn from the dark data. And for this, we want a pseudo label. It doesn't work very well when we use a pseudo label of the actions because there's no actions happening in the unlabeled dark data. So instead, what we do is pool different off-the-shelf models, maybe video text retrieval, sound source localization. Doesn't matter too much what the model is, just a few different things, pull them together, compress them into one pseudo label. And the idea is just to give any signal that can differentiate the videos in the dark. It doesn't need to be related to the action. It's more just to align the low-level features so it can work in both day and dark. And again, we notice the audio is really useful. So even if you can't hear, you can still kind of see it's hard to tell what exactly is going on in the video. And with sound, it becomes a lot easier to tell. So going back to this activity recognizer, so it works really well if we just leave this as a visual only recognizer. That's absolutely fine. But we can help it by also including audio. And we do this by first evaluating how useful the visual features are. This gives us some attention that tells us then how useful the audio is going to be later on. So we use this to adapt the visual features and reduce the domain shift. And also to then create this prompt that can tell us how useful the audio is going to be. So then the transformer knows, oh, the visual features weren't so reliable. We need a bit more audio in this prediction. And this helps a lot. So we were able to reduce the data dark gap quite a bit on a variety of different backbones and in different data sets. But where the model doesn't work so well is there's still this really large gap between the very high luminance and the rest of the videos. So there's still a lot of work to do here, as well as seeing whether this kind of model can work in different domain gaps as well. The other issue is, okay, we've managed to reduce the supervision requirement by making the videos task irrelevant. However, we still need a lot of these videos. So it's progress, but there's still a lot of videos we need to learn from. So with that, I'm going to conclude the talk. I'd like to thank particularly Fida and Yunhua. Fida led the two works I talked about on the self-supervision, and Yunhua the two on the domain adaptation. And if you want any more details, feel free to email me, check out my website. I'll also, as it said at the start, be starting at Leiden from September. So if you're interested in learning from limited labeled data, look out for some PhD openings.